a really exciting week, and we have two talks to finish off. The first talk is by Colm-cille Caulfield on Richardson number dependent bounds on buoyancy flux.
Okay, well, thank you very much, everybody, for coming back on a Friday afternoon to hear me talk. It's been a great program so far. I hope we go okay. Can you hear me, Michael?
Yeah, you're fine. We don't have a problem.
Okay. Well, what I want to talk to you today about is some work that has been going on for maybe 4 years with Rich Kurzweil, who's sitting in the front of the audience, and a really excellent former PhD student of mine, Wenbo Tang, who's now on faculty in Arizona State. Okay, and so here's what I want to talk about. I want to really try and get through these 4 points, really. Why am I interested in generating these bounds on mixing? Then I want to try and briefly introduce to you the method that we're using, this generating rigorous bounds. And it's rather intimidating, not only with the quality of the audience that I have at the back, but at the front, that I have Fritz Busser and Rich Kurzweil listening to me describing how the bounding theory works, but we'll see how we go. And we'll apply it to an unusual situation, a stratified plane couette flow, which is a nice model problem that allows us to investigate how much mixing might take, getting a bound on the mixing. And then we'll talk about what we find, the results, and in particular, we'll sort of have a bad news, good news sequence. We'll find that we managed to generate a bound, but know very little about it. And then we find that you develop a trick or a particular technique to find out more detail, in particular, to find out, if you ask the question, what is the largest amount of mixing that can take place in a stratified plane couette flow, we can identify the Richardson number at which that happens, which is a nice result. And then we'll talk about some of the conclusions and future directions. So, in this particular audience, it's not a really bit necessary for me to describe why we might be interested in small-scale mixing. It's an essential component of the ocean circulation. Of course, the issue that Michael so nicely talked about is shown in this sort of schematic picture from the Ferrari and Wunsch annual review paper, that it's hot at the equator, it's cold at the poles, and so therefore there is a thermal gradient that may be feeding into the mechanism by which you flow. There is also then got to balance the situation. There has to be some small-scale mixing process that manages to drive upwelling, and that then closes the circulation that's within the flow. Now, I don't want at all to get into the issue about whether it's being pushed by the thermal forcing or being pulled by the mechanical forcing. What is clearly important is the way that you parameterize, or the way that the mechanical mixing is parameterized has a great effect on the sort of upwelling that you observe. Depending on whether you say that it depends in some sense on the local stratification, the upwelling picture, the blue going down, red going up, is very different from if you just assume that it's uniform from these very nice simulations by Simmons. So, let's just try and fix the parameters that we're going to be interested in. We're imagining we've got some sort of stratified shear flow situation, that there's going to be variation of velocity and density. So we're going to suppose we have some characteristic scale of velocity variation, some characteristic scale over which it varies, d0, and some characteristic amount that the density varies. And so then, of course, you can define a bulk Richardson number, which would be the way you might want to parameterize this particular thing, in terms of the balance, of course, between the potential energy and the kinetic energy. And the critical thought experiment that I've always been interested in, and very much been driven by many of the people in the audience's work, is suppose you have a turbulent flow in a stratified environment. How much does it mix the profile? How much does it actually change the way the profile is set up? And we're trying to get some mathematical handle on how that might happen. Now, not saying that energetics is the whole story, but of course it is part of the story. And so therefore there's going to be the question is, how does the kinetic energy reservoir and the potential energy reservoir interact? Nicely set up by what Craig was talking about. So suppose you have some kinetic energy reservoir and somehow or other it's being forced. You can then see that there is a possible sink due to the buoyancy flux, because if you lift dense parcels up, you increase your potential energy in some way. And then there's also, of course, the dissipation rate that can be sucking energy out of your system. And as Craig was mentioning, even if there isn't a flow, you can imagine that you can have some injection of energy into the potential energy reservoir from the internal energy reservoir, which is sort of shown schematically here. If this is a temperature profile, it's hotter at the top, colder at the bottom, and you allow it to diffuse, then the potential energy of the system is going to increase even in the absence of the flow. Of macroscopic flow. But what I'm particularly interested in is saying, right, how big is this term compared to that term? That's the classic sort of question that motivates the oceanographic or the modeling exercise going on here. Because this is embedded in many of the models for diffusivity within larger scale models, because you can think about it, and the nomenclature is a mess, because you can think about it's often called the flux Richardson number, which is the ratio of the buoyancy flux, appropriately averaged, to the forcing that you have in the system, the turbulent kinetic energy production or whatever. And then there's these two quantities which are confusingly related, and having learnt at the knee of Mike McIntyre about lucidity, I really don't like this quantity gamma being called an efficiency because it can be greater than 1. Now, when I was a TA for a thermodynamics course, if the engine had an efficiency greater than 1, the student got a 0. So I think it's important to call this something else, a flux coefficient, the ratio of the buoyancy flux to the dissipation, and to call the mixing efficiency the ratio of the buoyancy flux to the two irreversible sinks, the buoyancy flux appropriately at long time average and the dissipation rate. And so I think it's important that I'll write these two quantities down. So gamma is B over epsilon, and eta, which is sometimes going to be called RIF, is equal to B over B plus epsilon, which of course is equal to gamma over 1 plus gamma. And that is equal to eta by 1 minus eta. Pardon?
I think Jim Riley agrees too.
Very good. Very sensible man, I've always thought. Yes.
Craig agree?
Yeah.
Craig,
So,
do you agree?
In principle, for sure, but I don't know many processes where B is greater than E, so it's pretty much mostly less than 1 anyway. So
That's the word
absolutely.
efficiency, like the Colm said.
Fair enough.
Yeah.
Absolutely.
Okay, so what is then important about, what's nice to appreciate about these particular quantities is that they're inherently related. An understanding of how the flux Richardson number or the mixing efficiency behaves then tells you something really useful about the eddy diffusivities. And this really nice work from Breutauer, I can't pronounce that name, and Limburg about the diffusivity is showing how important these sorts of parameterizations are. But what I really want to draw your attention to is if you want to know stuff about the diffusivity of heat and momentum, you really want to understand how the mixing efficiency depends on the overall stratification. Now, the standard model, I would say, is due to Osborne, which is a very, very influential paper from 1980, which basically says that this quantity, gamma, is a constant, in some engineering sense, less than or equal to 0.2. But if you actually read that paper in detail, where that comes from is the PhD thesis of Rex Britta, which I actually have here. And just for the students in the audience, the title of this thesis, look at the size of it, is An Experiment, singular, on turbulence in a density stratified fluid. One single experiment. However, on page 837, as we all know, there is where this particular result comes from, where he actually applies to his data the model of Ellison, which is essentially saying that if you look at this, the mixing efficiency is less than or equal to this ratio of the decay timescales of the turbulent kinetic energy to the density fluctuations. And there's two competing factors going on in this expression. One is, as the stratification gets stronger, the belief at that time was that you would suppress the transfer to vertical velocities, and so therefore you'd expect this number 3 to get larger than 3 and go down to 5, so on, and so make this quantity smaller. Yet his data showed him that as stratification increased, the timescale over which fluctuations in density decayed was smaller than the timescale over which the velocity fluctuations were falling, which really links with the Lindborg simulations, because you can still have significant amounts of velocity variation. And that then means that this mixing efficiency might well be bigger than a third, because it makes this quantity small compared to that. So if you actually drill in, basically Rex says that he thinks, well, there's one effect that will make it bigger, one effect that will make it smaller, so he'll leave it at the value he measured. But I think that's a fair representation. But then if you look at the data about how gamma, this mixing efficiency, varies with Reynolds number, this line here is assuming gamma is equal to 0.2, looking at the eddy diffusivities compared to this is the buoyancy Reynolds number. And you'll see if gamma was equal to 0.2, the data should follow the red line. And since this is a logarithmic plot, I really don't think it's really a very strong evidence. There's also De Bruyne-Kops and Riley's nice simulations. This quantity here is gamma, and these are simulations for different Reynolds numbers. And you'll see when for the largest Reynolds number calculation they reported, the one up here, the flux coefficient is substantially above the 0.2 sort of value, and so there is evidence that it can be somewhat larger. The experimental data is uncertain. This is the Fernando's review. This is the mixing efficiency against the overall stratification. It rises up towards about 0.2, and then something odd happens at higher stratifications. Collected experiments collected by Paul Linden from the 70s shows that this mixing efficiency, the flux coefficient, is not only a function of Reynolds number, but also a function of J, the overall stratification, because it goes up to a value of about 0.25 and drops down. And then observations and measurements by Joe Fernando and his group with Pardiac shows also that, once again, the flux coefficient, the data goes up to some value here. Indeed, the mixing efficiency is of order 0.4 or so, and then drops down again. And there is a Richardson number, overall stratification, where it peaks. And once again, this is experimental data, this is observational data. It may be difficult to see at the back of the room, but it goes up to a larger value and drops down, and it certainly doesn't fit the standard parameterization of Miller and Yamada that it saturates at around about 0.2. So really, what I've tried to say in this whistle-stop tour through the evidence is, it's not clear that gamma is constant, and the data appears to show that gamma depends both on overall stratification, J, and Reynolds number. And indeed, perhaps most of you would think that's not a particularly controversial thing to say. But then the question is, can we get a bound? Can we construct a mathematical argument to say, well, that gamma or the buoyancy flux can have a particular value? And the particular angle we're going to take is, if we assume the flow is maximizing the buoyancy flux, is mixing as much as it can, what does that imply for the overall stratification and the value of these quantities? So we're going to look at a very simple model flow, because it was one that Rich knew how to find the solution for, which is we look at a stratified Couette flow. So what we're doing here is we've got two plates, one held at a constant density. You can imagine, think of the constant temperature. And so in particular, like what Craig was saying, the gradient, the flux through this system is part of the solution, not imposed. And we're also imposing a constant velocity at the boundary. So the amount of forcing is part of the problem too, because the amount of energy we put in depends on the local gradients. And we assume that the flow is very high. We're going to go to the higher Reynolds numbers. We're going to assume it's statistically steady. And for the simplicity of my presentation, we're going to assume the Prandtl number is 1. That introduces complications that we don't want to get into. Therefore, we have two obvious parameters. The Reynolds number, which is essentially the speed at which we drive the plate, and the Richardson number, overall Richardson number, which is like a measure of how strong the coupling is between the density field and the velocity field. So if we scale our equations on the diffusive time scale, you get the Navier-Stokes equations and a diffusion equation. And essentially what you want to then think of is increasing Reynolds number increases the speed at which you push the plate, and increasing the overall stratification increases the coupling between the velocity field and the density field through this term. That's really the way these equations are behaving. Okay, And now the problem we want to do is we want to construct rigorous bounds. We want to find a bound on the buoyancy flux within this system. And there's a great history of this. There's one approach that Howard and Busse did, and then During and Constantine developed the background method, which is what we're going to do. Rich showed that in certain circumstances they were dual problems. But really what I want you to understand is we're going to look at the buoyancy flux, appropriately time average, which within our system is this quantity. And because of the statistical steadiness and the boundary conditions, it is also up to just a simple constant, which is like the steady diffusion of the conductive state, is related to this is like chi as well, really. You know, it's the dissipation of density variance. And what we want to do is we want to maximize the buoyancy flux subject to certain obvious physical constraints. We want to conserve energy, conserve the total amount of heat going through the system. And we also want to look for solutions that have the right streamwise momentum balance and the right heat balance that you would expect the solutions to the Navier-Stokes equations to have. But the trick we want to follow, the idea we want to follow, is actually search in a broader class of functions than the solutions to the Navier-Stokes equation. This is the core idea of this technique. So imagine this is the solution space. So the solutions to the Navier-Stokes equations and the heat equations that satisfy the boundary conditions are incompressible all live here. We're going to search in this class, which is a whole set of solutions that are incompressible, satisfy the boundary conditions, don't necessarily satisfy the Navier-Stokes equations, but satisfy these constraints, which of course solutions to the Navier-Stokes equations do satisfy. And so then if we find a solution in the red oval phase space, well then we've definitely found a bound. So if we can say all the mountains of the solutions are only at most this high in the red mountain range, well then that is a bound for the blue mountain range because it's a subset of the solutions we're searching over. And it's actually easier to find solutions in the broader class because what we do is we impose these constraints by Lagrange multipliers. So let's talk a little about how we do that. And both the way we impose the constraints and deal with the boundary conditions is we allow ourselves to consider an unusual decomposition of the velocity and density field in this particular way. And it's non-unique, and since it's non-unique, we're then able to take variations with respect to it. Let's think about, we decompose the velocity field into a constant component that is a function only of z, and fluctuation. And similarly, we decompose the density into a component that's only a function of z and a fluctuation away from that, such that the background part satisfies the boundary conditions, and so the other parts have homogeneous boundary conditions, and yet they're non-unique choices. So here is an example of two such choices. Suppose, and indeed this is very much what the density field looks like, this is actually what the density field looks like. A boundary layer, well-mixed interior, boundary layer. Well, then we have an infinity, but two perfectly adequate choices of this decomposition are the solid lines. That's the tau field, background, function only of z, and satisfies the boundary conditions. And if we add that to this guy, we'll get the green line. But also the dashed choices are fine. This satisfies the boundary conditions. And if we add that and that together, we get the green line too. So we have these two different choices of fields to take. And then we want to maximize the buoyancy flux. And so then we impose, using Lagrange multipliers, we impose the total kinetic energy balance. A by phi dash, and remember that's the background field, it's gradient, but now it acts as a Lagrange multiplier that imposes the streamwise momentum balance. AB, which we just choose for, is B, is another constraint, which imposes the entropy balance, and AB tau primed imposes the horizontal heat balance. And of course, pressure imposes incompressibility. And so we use these Lagrange, then we can take variations of this expression with respect to all the fields. We can represent the U's that I've written down here in terms of phi and V, and we can take variations with respect to A and B. We can take a whole pile of variations, get a whole messy lot of Euler-Lagrange equations, and then we can find our solution. Now, if you take the first two, if you just take variations with respect to the mean components of the fluctuation and the mean components of the density, you end up with this substantially simplified expression. And what we have here is then we can say, well, this is what we want to maximize. And so by inspection, we can tell we can find a bound for this if we can prove this quantity h is always positive. And if we can prove it's always positive, well then or non-negative, when it's 0, we then have the bound, because then if this is always positive. So that's a nice way to set it up, and that's what we need to do. And by inspection, you can see for all possible choices of fields, well, we have to make sure that A is then positive, so that this term for a particular choice of field is positive. And similarly, we have to make sure that A is less than or equal to 1, because otherwise we'd have a positive definite quantity multiplying a negative quantity, and we'd have a problem. So we have simple things by observation. But if we then say let A go to 1, we then see that actually the spectral constraint just corresponds to energy stability on an unstratified flow. And so then we can say, oh yes, that's a way to find a solution. So we start from this particular solution. We start from the flow being conductive, the laminar profiles all to start with, and then we increase the Reynolds number. We find that the Reynolds number where it stops being energy stable, so fluctuations don't necessarily die monotonically, we find a new solution, and we follow that solution, ensuring that it satisfies the spectral constraint. And so what we do then is we add more and more modes with, we assume streamwise invariance because it seems to work. We've checked it's okay otherwise. And we add more and more modes with span-wise variation, which have particular wave numbers that come in through bifurcations. And each of those bifurcations occurs when we need to modify the background flow such that the spectral constraint remains satisfied, which is effectively an eigenvalue problem. We have to make sure a sequence of eigenvalues remain positive, and we essentially build a solution that has a set of embedded boundary layers like the Bosso problem. But what is not nice about this is that this is the solution that A is equal to 1, and we're able to work out the buoyancy flux for this particular flow. We see that it scales with the Reynolds number cubed, which means that it's dimensionally a flow. It's an inertial scaling, which means that the the flux coefficient for this particular guy is 0.5, tends towards 0.5, a finite value, or eta tends towards 1/3. Here's the plot of the gamma as Reynolds number increases, but it's degenerate. The problem is, thank you. The problem is that we lose all knowledge of the density field when A is equal to 1, because all the coefficients that involve J have A equal to 1. So we can find a bound, and we know what the velocity field is, and we know what the mixing efficiency is, but we can't say anything about what the flow is. So how do we break that degeneracy? And how do we talk about it in 5 minutes? So what we do is we say, okay, we're going to search across all possible solutions with varying, we're going to make a new control parameter, the flux coefficient. And by making the flux coefficient a new control parameter, we're going to say the solutions we're interested in are solutions that have a particular coupling between the buoyancy flux and the dissipation. And then we're going to find, I hope that will then break our degeneracy. And so now we're looking over a class of things that has this particular coupling constraint, and that then means that the solution has this coupling in the solution we find will inevitably have this coupling. But if we're able to find the solution for all values of coupling, then we can turn down the coupling and approach the actual solution we found before in the limit as we make the coupling breakdown switch off. The coupling is imposed by a Lagrange multiplier called C, which then switches us down, we switch it down to 0. So now the problem of interest is exactly the same, except now we've added in this extra constraint which couples the buoyancy flux to the dissipation through this constraint C, this Lagrange multiplier C. So the limit we want to take is C tends to 0. And now we do exactly the same problem, and we can see that then we need for the quantity we want to bound to be positive, to be a bound, we have to have this H quantity to be non-negative, which now means that the quantity A is positive, and this new grouping D has to be positive because of this coefficient on the fluctuations in the density field. So now we hope we're able to break the degeneracy, which I think we are. because we now are able once again to continue our energy stability calculation, and we're able to find the new solution, but I'm rushing on to give you the answers. The situation is we now are able to find the behavior of the solution at a particular Richardson number. We then have broken the degeneracy, and we find that at a given Reynolds number, as we increase the Richardson number, we increase the buoyancy flux. And if we then plot, the same plot we plotted before was the buoyancy flux against the Reynolds number without this constraint, and then we impose different values of gamma with this constraint, we find that this curve actually is traced out, is a tangent bundle to all these other solutions with different values of gamma. So for small values of gamma, it's for the small Reynolds number. And then as you get larger, it's gamma equals 0.5, which is the asymptotic solution we found before. But we're able to identify what Richardson number is associated with each of these particular profiles. So now we're able to say how the Richardson number varies with Reynolds number for this thing that grows most rapidly. And we find out that the one that has the highest bound has 0 Richardson number at small Reynolds number, and then it increases, and for this particular setup, it increases towards 1/6. And so asymptotically, we have now identified what the Richardson number of this bounding solution is. It is 1/6. And we're able to understand, as we increase the Reynolds number, we're able to identify a way to find this most unstable mode. We are able to construct these lines, these colored lines. This green line is the set of solutions we find for Reynolds number 4/3 of the energy stability. This blue line is the set of solutions we find with all the different possible coupling parameters for Reynolds number twice the energy stability, 4 times, and then the asymptotic infinity. So we construct these lines and then search along those lines to maximize the buoyancy flux, and then we can then identify the properties of the solution on the particular, at the most unstable, the one with the highest bound, the highest buoyancy flux. We're actually able to identify its Richardson number, and it's of this order about 0.16 or so, which was interesting to me. What are the properties of the solutions? We now know everything we want to know about the solutions. We know that we have very strong velocity boundary layers near the side and a weak velocity gradient in the middle, and a perfectly well-mixed interior for the density field, with very strong gradients in density at the boundary, but still nevertheless they're regions where they have order 1 over Reynolds number boundary layers. They're about, they are still very, very low Richardson numbers in the boundaries, 0 Richardson number in the middle. And we have now managed to identify a global maximum for the buoyancy flux. This is a contour map of the buoyancy flux for varying J at very high Reynolds number against this mixing efficiency. And then we find that then for a particular mixing efficiency, the most unstable, the highest bound we can find is when J is 1/6 and the mixing efficiency is 1/3. And that seems to be the one that has the largest possible growth rate, though you see all the others are around. And what is the property of this particular solution is that there is a subtle coupling between the streamwise velocity fluctuations and the vertical density fluctuations. Because it really seems to say that what you want is to have the velocity fluctuations V1 just perfect to interact with V3 so that you get a lot of turbulence production through the Reynolds stress, and yet your theta field, your density field, to also have exactly the same structure, to be very well coupled with the vertical velocity field so that you get a lot of mixing. And the best possible combination you can get is for this Richardson number around 1/6, which we've managed to break the degeneracy, because even though we can't go outside here within our calculation mechanism, we know that is that is the solution with the highest possible buoyancy flux. So, in the model flow, if the flow is maximizing its buoyancy flux, we know that gamma, the flux coefficient associated with it, goes up to about 1/2, which is associated with an asymptotic mixing efficiency of 1/3. We know that the maximum possible buoyancy flux bound occurs at this particular finite Richardson number. Nothing to do with Miles-Howard. We're just saying that is what we know. That is absolutely the best possible case. If the Richardson number is less, we don't mix enough. If it's more than that, we can't find the solution doesn't work. it seems a reasonable value, but are the bounds too tight? We've got are tight at all, because we have a numerical prefactor too, not only the scaling. We say it's good scale on the inertial scale, u cubed over d, but we now have a particular prefactor. We have no idea what it is. So what is the effect of varying the Prandtl number, and what happens to the solution when you go beyond this particular choice? When you go to larger Richardson numbers, how does it drop off? What is the right-hand side of the Linden curve? So, thank you very much.
Well, I think we've got plenty of time for questions. I know Mike McIntyre has a question, but Dr. Busser first.
Yeah, I'm interested to see that you have this finite shear in the interior,
Yes.
which you of course also have in the unstratified case. But how does it change with the Richardson number? I mean, if you were talking about if you consider other cases with larger or lesser Richardson number, does it change?
With the velocity field does change with Richardson number. The picture I showed you is the one that is the choice, which is the one where you, for that particular value of gamma, that you maximize the buoyancy flux. And if you look carefully at the fields, what actually appears to happen is that the situation where you maximize the buoyancy flux is the instant precisely where the density field in the interior goes exactly vertical. And so the velocity, there is a coupling between the mean velocity field and this. So the mean velocity field shallows up rather, until the instant when it causes the middle density field to be exactly marginally stable. And then it can't go beyond that. And so that is the dependence on the stratification. It is weakened by the stratification until the instant when it has caused the stratification to be homogeneous in the interior, and then it locks.
This gamma infinity equals a half is sort of amusing for me, because long ago I did a sort of slightly naive thought experiment about breaking gravity waves. I still think it's somewhat relevant to real breaking gravity waves in the mesosphere, and found the maximum possible gamma was a half in that thought experiment. You would take a gravity wave of huge amplitude and you let it suddenly overturn and perfectly mix, which is a rather idealized thought experiment. But I got that half, but then more interestingly, for more realistic amplitude, the second point is that the gamma you got was highly sensitive to the amplitude you assumed, to how well past the breaking threshold you assumed. And if you took it only slightly above the breaking threshold, as with a spilling breaker, gently breaking waves, gamma could easily be more like 1/100th.
Absolutely.
It's absolutely sensitive. This was published in JGR in 1989.
Yeah. This argument is that this is mixing as much as it possibly can. We're maximizing the buoyancy flux. We're not the bound on the buoyancy flux. If this is a real flow, is doing the most it can. We're driving it like crazy. We've got very low Richardson numbers everywhere. And in that case, you can then get to gamma equal to half, but no further.
So, do we have any more questions? Yeah.
In terms of the boundary layer that you described with your solution, do you have any overshoot phenomenon? That is, does it go from, is it a smooth curve, or does it go perhaps to have a shape where the gradients are exceeding the value that you had?
Well, that's at the very high round number. I'm a little nervous about drawing such fine detail into the structure of our solutions, because sometimes we have observed that, but I'm not entirely sure that it's not a numerical problem. Because we're representing the solution in terms of a really relatively small number of modes. So if you see a structure like that, I'm not entirely sure it's real. But because we're of course we've always been, because what we're doing is we're doing a continuation problem on a set of nonlinear equations that we're representing with a sort of collocation method. And the thing is, this problem is somewhat different from other versions of this, because we can continue with J, we can continue with gamma, or we can continue with Reynolds number. And the issue is there was some odd numerical issues about which order you did when you said you converged to a solution that would look subtly different in its fine detail in the boundary layer. Because of course what we were actually interested in was an integrated quantity which was not so sensitive to that fine structure. It's a very good question.
Okay, I think we should move on to the next speaker, so let's thank the speaker.